Someone walks up to you and says, "Build me an AI agent." And you open a blank file. What do you write first? Most people reach for a framework. They start typing code. That is the wrong instinct. Before you write a single line, there are 5 design questions you need to answer. And those 5 questions will determine whether your system is something you can trust, scale, and hand to someone else, or something that breaks the moment it leaves your laptop. This is episode 2 of Building YUYUTSAVA, System Architecture and High-Level Design. Let's start with how to think. Imagine you've just hired a brilliant new engineer on your team. They are genuinely capable. They can read any file in your codebase. They can run scripts, call APIs, write code, delete code. But before you give them access to your systems, you stop and think through a few things. What can they break? What should they be allowed to do unsupervised? How will you know what they did? This is exactly the mindset you need when designing an AI agent system. The agent is your new brilliant engineer. These 5 principles are the design decisions you make before you hand it the keys. Principle 1. Design for what can go wrong before you design what should go right. In traditional software, you design the happy path first. Edge cases come later. In AI systems, that order is reversed. Your agent is going to make decisions you never programmed. It will take actions you didn't anticipate. That is the whole point of building an agent. It's supposed to reason on its own. So the first question a solution architect asks is not, "What should this agent do?" It's, "What is the worst thing this agent could do? And is my system designed to contain it?" Design your safety boundaries first. Every capability gets built inside those walls, not the other way around. Principle 2. Every layer in your system should be connected to the next layer by a contract, not an assumption. Here's a simple way to think about it. Your computer doesn't know and doesn't care how the screen lights up its pixels. It sends a video signal. The display handles the details. If you replace your desktop monitor with projector, your computer doesn't need to be reprogrammed. The contract, video signal in, image out, stays the same. That's what a good interface between layers looks like. Applied to your AI system. The engine that builds your agent should not care which large language model you're using today. It only cares that it gets an object that satisfies a certain interface. Today that interface is Grok. Tomorrow it could be Anthropic, or a local model on your own hardware. Want to switch providers? Change one file. Nothing else in your system breaks. That is what designing by contracts gives you. Replaceability without fragility. Principle 3. Capability and permission are 2 different things. Keep them in separate layers. Again, your new engineer can technically email anyone in the company. The system gives them that capability, but you would never want them emailing clients on their first day without a review. That's a permission decision. The same applies to your agent. The agent might be capable of deleting files, running any shell command, calling any external service. But what it is actually allowed to do, without a human confirming first, that is a completely separate design question. If you mix capability and permission into the same layer, they become impossible to change independently. Permission policies change faster than capability code. A trusted internal environment has different rules than a public-facing deployment. Keep them separate. Each one should be replaceable without touching the other. Principle 4. Your agent runs a loop. Every loop needs a governor. A chatbot takes one request and returns one response. It's a single function call. An agent keeps going until it decides it's done. What happens if it never decides it's done? In a traditional program, an infinite loop is a bug. In an AI agent system, an infinite loop is an expensive bug. You are paying for every token the model generates. You are paying for every tool call it makes. Your architecture must include a hard stop, a recursion limit, a timeout, something that says, no matter what this agent decides, it ends here. This is not an optional feature. It is a structural requirement of any agentic system. Principle 5. Build for what you can see, not just what works. Your agent will make decisions you didn't write. When something unexpected happens, and it will, you need to be able to trace exactly what occurred. Which tool did it call? What was the input? What did the tool return? What did the agent decide to do next? If you can't answer those questions from your logs, your system is not finished. It's just lucky. Observability is not a debugging afterthought. Design it into the core. Build the ability to stream every decision, every tool call, every result. Because you can't fix what you can't see. 5 principles, not specific to any framework, not specific to any language. These apply to every AI agent system you will ever design. Now let's look at how YUYUTSAVA implements every single one of them. This is the full high-level design of YUYUTSAVA. 7 distinct layers, each one with a defined responsibility, each one connected to the next by a contract. User at the top, execution backends at the bottom, and in between, the harness that makes the whole thing safe, observable, and replaceable. We're going to walk through each layer, what it does, and why it was designed that way. Let's start at the top. The user types a task on the command line. YUYUTSAVA receives it. The CLI layer does exactly 3 things. It parses the arguments, it loads the environment configuration, and it selects the execution mode. That is it. Nothing more. The principle of a well-designed entry point is this: parse, configure, delegate. The CLI layer does not know how the agent works. It does not know which tools exist. It does not know what the model will decide. It receives the task, sets up the configuration, and hands it off. That is the full scope of its responsibility. Everything else, what model to use, what backend to run, how deep to recurse, those are configuration choices passed in as flags. The CLI reads them and passes them down. All these providers implement the same interface, that is LLM settings. The engine never talks to Grok directly. It never talks to OpenRouter directly. It only ever talks to the LLM settings interface. Want to switch providers? Set one environment variable. Nothing else in the system changes. No code touched, no tests broken. Today it is Grok. Tomorrow it could be OpenRouter, or a local model running on your own machine using Ollama. The system does not care. It only cares about the contract. That is principle 2. Design by contracts, implemented at the very first decision point in the architecture. Below the CLI is the engine. The engine has exactly one job: take the large language model, the execution backend, and the system prompt, and assemble the agent. In engineering, this pattern is called a factory. It takes in parts. It returns a finished, ready-to-run product. The function is called build agent. It wires together the LLM, the backend, and the system prompt, and returns a fully assembled agent bundle ready to receive tasks. The CLI doesn't assemble the agent. The tools don't assemble the agent. The safety layer doesn't assemble the agent. Only the engine does. One place where assembly happens. One place to change when the assembly logic needs to evolve. That is a good design. Centralized assembly. Clear ownership. Now here is where most people building AI systems make a critical mistake. They scatter safety logic across the code. A check here. A guard there. A validation buried inside a tool function. YUYUTSAVA treats safety as a dedicated architectural layer. A harness. Before the agent starts running, every request passes through this harness. 2 components. 2 distinct responsibilities. The tool filter middleware controls what the agent can see, not which tools exist in the system, which tools the agent is aware of in this specific session. You can run YUYUTSAVA with web search enabled or disabled. You can expose only file operations or only skill execution. The agent sees exactly what the configuration allows. Nothing more. The permission middleware does something more direct. When the agent attempts a dangerous action, running a destructive command, writing to a sensitive path, the loop pauses. The system surfaces the action to the user, right there on the command line. It says, the agent wants to do this. Is that okay? Now that is the HITL or human-in-the-loop strategy we are using here. The user decides. Yes or no. Only then does execution continue. That is principle 1. Design for the worst case, implemented as a concrete layer in the architecture. And because this is a dedicated layer, separate from the engine, separate from the tools, you can replace it. Run in a fully trusted environment, swap in a permissive policy. Deploy in production, swap in a more restrictive one. No changes to the agent logic. No changes to the tools. The harness is the architecture's answer to principle 3. Capability, in the agent. Permission, in the harness. Always separate. This is the heart of the system, the agentic loop. In episode 1, we introduced the react pattern. Reason, act. Observe, repeat. This is where that pattern lives as concrete code. There are 2 nodes. First is the agent node, where the large language model looks at the current state and decides what to do next. And second is the tool node, where the decided action is actually executed. The agent node produces a tool call. The tool node executes it and returns a result message. The agent node reads that result and decides what to do next. This is not a pipeline. It is a state machine, a loop with memory. The framework managing this loop is called LangGraph. LangGraph lets you define agents as explicit state machines, not callbacks and event handlers. An actual graph with named nodes, named edges, and clear decision logic. This matters for two reasons. You can reason about the loop. You can test individual nodes in isolation. And you can replace any node without touching the others. That is a design that ages well. And here, principle 4. The loop has a governor, a recursion limit. By default, 200 steps. If the agent has not completed its task in 200 steps, the system stops it, cleanly, with a clear message to the user. The loop does not run forever. The architect decided that up front, as a structural constraint, not as an afterthought. Now we reach one of the most interesting design decisions in YUYUTSAVA. The tool layer. Every agent needs tools. Read files, write files, execute commands, search the web. These are the actions the agent takes in the world. A naive design hands the agent every tool at startup. Load them all. Let the agent pick which ones to use. We are not going to do this. At startup, the agent has access to exactly one tool. It is called tool search. That is it. One tool. Not 10. Not the full library. 1. Here is why. Every tool you give an agent takes up space in the context window. The context window is the large language model's working memory. It is finite. It is shared between the task, the conversation history, tool schemas, and the model's own reasoning. If you load 50 tools at the start, you have consumed a significant portion of the model's working memory before it has even read your task. That is a real performance cost. Instead, the agent discovers tools on demand. It reasons, I think I need a file reading capability. Let me search for it. Tool search returns the exact schema for the tool it needs. The agent loads it, uses it. The schema is released when it is no longer needed. This is called lazy schema discovery, and it keeps the context window clean throughout the entire task. The tools are organized into 3 families. First, the task runner tools. Read, write, delete, execute, and ask user. These are the core operations for working with files, the shell, and the user directly. Second, the web search tools, powered by Tavali and Exa. These give the agent access to live information from the internet when web search is enabled. Third, the skill tools. These let the agent load and execute pre-written workflow patterns, reusable skills defined in files that can be discovered and run on demand. And the tool filter middleware we saw earlier, sitting in the safety harness, controls which of these families the agent is even allowed to discover. The agent can only find tools that the middleware permits. Principle 3. Capability separate from permission, enforced all the way down to the individual tool family. Every tool call the agent makes has to run somewhere. That is what the execution backend does. YUYUTSAVA has 2 backends, the local shell backend and the Docker sandbox backend. The local shell backend runs tools directly on your machine, your actual file system, your actual shell. When the agent reads a file, it reads a real file. When it executes a command, it runs on your real system. Fast, direct, and exactly as consequential as it sounds. The Docker sandbox backend runs tools inside an isolated container. Same tools, same commands, same interface, but the agent's workspace is contained. If the agent tries to delete something important, it deletes something inside the container. Your actual machine is untouched. The container is thrown away when the task ends. Here is the key design point. Both backends expose exactly the same interface to the agent. The agent does not know, and does not care, whether it is running locally or inside a Docker container. You switch backends with a single flag. Execution Docker. The entire agent, the entire tool layer, the entire loop stays exactly the same. Principle 2. Design by contracts. The backend interface is the contract. The implementation, local or isolated, is swappable. Step back and look at the whole picture. Every single layer in this system is independently replaceable. New large language model provider? Add one class that implements the LLM settings interface. Nothing else in the system changes. New tool family? Add it to the tool registry. The lazy discovery system picks it up automatically. The rest of the system never needs to know it exists until an agent asks for it. New execution environment? Implement the backend interface. Pass it in at startup. The agent runs exactly the same way it always did. New safety policy? Swap the middleware layer. The loop doesn't change. The tools don't change. Only the harness changes. YUYUTSAVA started as a command line tool. In later episodes, we will extend it into a full async platform with API server, session management, async runtime, and memory layers. That extension is possible because the design was right from the beginning. Not because we planned every feature in advance, but because each layer knows as little as possible about the others. Small things designed properly. That is what makes the overall design scale. So in this episode, we covered the 5 design principles, 7 architectural layers, and complete high-level design of YUYUTSAVA. Every decision made for a reason you can trace back to the first principles we covered today. In the next episode, we open the code for the first time. We'll look at the agentic loop as it's actually implemented in LangGraph, the state machine, the nodes, and the decision edges that make it all work. Subscribe so you don't miss it. See you in episode 3.